Okay, and finally, we're going to look at one application of the chain rule. So we are going to apply the chain rule to for implicit differentiation. Right, so suppose that is defined implicitly as a function of x and y. Right, so it means that we have some equation on x, y, and z. I'm going to give you an example of such equation. So, for example, we have this equation. So x z square plus yz, sorry, plus yz plus cosine of x minus y is 0. Okay. Now, here, if you look at it carefully, you will see that this is a quadratic equation in z, right? So this is the coefficient at z square, this is the coefficient at z, and this is the constant term. So which means that hypothetically speaking, we could just solve it, right? So the discriminant is what is the coefficient at z is y squared minus 4 times the coefficient at z squared is x times cosine of x minus y, and z is going to be minus y plus minus square root of the discriminant y square minus 4x cosine of x minus y divided by 2x. So it means that this equation it defines actually two functions, well, two different functions for z, as functions of y and x. So one is with plus, the other with minus, right? But the point is that here we can't solve it. So I mean, but sometimes we can't. So very simple example. So what if I wrote z to the 5 instead here, right? So then we couldn't solve it for z, but still, you know there is a relation between x, y, and z, and since there is a relation, essentially we can think of z as a function of x and y. The idea here is, I mean, what if we want to find the derivatives of z with respect to x and y without solving the equation? And here is how we can do it, right? So we can just take our function f and differentiate it. So notice that the derivative of a constant is 0, right? So when we differentiate a constant, we are going to get 0. So now, applying the chain rule to differentiate this equation, we will get just this, right? Um, at the same time, so notice that the idea is that z is a function of x and y. So z is the dependent variable, and x and y are independent variables. So it means that dx is just one, right? So we are differentiating x with respect to itself. And dy dx is going to be 0 because y is an independent variable. It does not depend on x. So, and by just using this information, we get this equation on dz dx. And then we can make it subject and we can solve for dz dx. Right? So solving this for dz dx, we just get this. So the dz dx is minus df dx over df dz, and the similar expression for the dz dy. Okay, so how can we apply this? So this is the conclusion. So this is what you should remember. I think you can just memorize it, but here it is fairly simple to derive this equation. So maybe it makes more sense to, instead of memorizing the end result, you can try to make sense out of the derivation of this main result. And on the exam, you can just always, and then if you forget it, you can always just repeat the same steps and figure this out. So how can we apply this? So here is a specific example. It is fairly straightforward. So let me just do it. So the derivative of z with respect to x is going to be minus f differentiated with respect to x divided by f differentiated with respect to z minus, okay, so this is my f. So its derivative with respect to x is what? 3x squared, y cubed, z cubed 0, so plus 6yz divided by the derivative of f with respect to z. So 3z squared plus 6xy. Well, if you want, you can just, I don't know, simplify it. So it can be cancelled by 3. So minus x squared plus 2yz divided by z squared plus 2xy. Well, the same for y. So the derivative of z with respect to y is minus fy over fz. And this is going to be minus 3y squared plus 6 xz, I believe. This is fy, and fz is just the same. So 3z squared plus 6xy. Well, if you want, you can simplify it too, but here is just the end result. All right, I hope it makes sense. And this is the last example in the lecture. So now you can just try to do the last quiz, and that's it for today.